Look up on a clear night and find the faintest star you can see. It is likely a sun much smaller than ours. It does not draw attention at first glance. It gives a steady light that is softer than the glare of larger stars. If you look long enough, your eyes settle. The sky steadies with it. The light arrives after a long journey, crossing empty space without sound. You can imagine that the star is simple. It is not. It is quiet because it is patient. Tonight, we follow one red dwarf from its beginning to its long, slow prime. Long before this star shines, a cloud of gas and dust drifts through the galaxy. The cloud is cold. It is made mostly of hydrogen and helium. Tiny grains of dust mix with the gas. Gravity works on every piece, very gently, all the time. In some places, the cloud is thicker. Where it is thicker, gravity pulls a little more strongly. Slight differences grow. The gas starts to drift toward the thicker patches. The motion is slow, but it continues. The flow is not smooth. The cloud has small movements and waves. Some parts compress, while others spread out. The compressed parts cool by giving off faint radiation. Cooling lets them sink deeper into gravity's pull, which leads to more compression. A fragment forms. It is the seed of a star. Inside the fragment, the gas falls inward. As it falls, it speeds up and heats up. Gravitational energy becomes heat in the gas. The center grows warmer and denser. The region around the center becomes thick with particles that trap radiation. Heat cannot escape easily. Pressure rises. The collapse slows in the center and continues in the outer layers. A small embryonic star forms at the core. It is not yet a star by the strict rule of fusion, but it is a real object. It glows by the heat of its own contraction. The glow is mostly an infrared light that our eyes do not see. Around it, there is a disk of gas and dust. The disk forms because the original cloud fragment had a little spin. As material falls in, it keeps that spin. Conservation of angular momentum turns a cloud into a disk. The disk is thin compared to its wide reach. It is the place where planets can grow. Dust grains bump together and stick through small forces. They make clumps. Clumps gather more dust, and they turn into larger bodies. In the inner regions of the disk, the heat from the contracting protostar keeps water in vapor form. Rock and metal grains dominate there. Farther out, water and other ices can survive and join the solids. Over time, many small bodies collide. Some break apart, some grow. This process takes millions of years. It does not happen all at once, and it does not happen exactly the same way in every disk. But the physics of sticking, collision, and gravity makes growth possible. Our red dwarf is still gathering mass from the disk at this stage. Streams of gas slide along magnetic field lines from the inner edge of the disk down onto the young star. Each stream hits the surface and heats a small spot. The star rotates. The hot spots come and go. The star also drives jets of gas along its rotation axis, guided by magnetic fields. The jets carry away some of the angular momentum and help slow the spin. Inside the young object, energy moves by churning motion. The gas is opaque and cannot carry energy outward easily by radiation. Rising and sinking parcels of gas do the work instead. This is convection. In a low-mass object like a future red dwarf, convection can fill the entire interior. That is important for its later life. For now, The churning brings heat outward and allows the object to settle slowly. The core grows hotter and more compressed as the infalling material adds its weight. At a few million degrees, fusion of deuterium begins. Deuterium is heavy hydrogen with a neutron in the nucleus. Its fusion happens at lower temperature than ordinary hydrogen. This brief phase provides an extra source of heat that slows the contraction. It acts like a temporary cushion. But deuterium is rare. When it runs low, the contraction resumes. As the protostar continues to contract, the inner regions get hotter. The pressure in the core increases. The central temperature approaches the threshold needed for ordinary hydrogen fusion. The exact threshold depends on the internal conditions and the balance between pressure and temperature. In an object that will become a red dwarf, that threshold is reached only when the mass passes a certain limit. If the mass were smaller, the core would never get hot enough. It would become a brown dwarf. Our object has enough mass. The core grows hot enough for hydrogen to begin turning into helium through the proton chain. A small rate at first, but enough to matter. When fusion begins, contraction slows and then stops. The heat from contraction is no longer the main source of energy. Fusion takes over. The star arrives on the main sequence. Reaching the main sequence is not a sharp moment. It is a settling into balance. Gravity pulls inward. Pressure from hot gas and radiation pushes outward. The two are equal. The star no longer shrinks. In a red dwarf, this balance is especially steady. Fusion in the core releases energy. That energy must reach the surface to leave as light. In this star, energy rides upward on convection. The whole star turns over from center to surface, like water in a gentle simmer. Because the whole interior is convective, fresh hydrogen from the outer layers circulates inward. Helium produced in the core circulates outward. The fuel is shared throughout the star. This is crucial. It means the star can use almost all of its hydrogen before fusion fades. Larger stars with radiative cores trap helium in the middle and keep hydrogen locked in the outer layers. Red dwarfs do not. Their mixing makes their lives long. At the surface, the star shows the marks of convection and magnetic fields. The star rotates. Rotation and convection together feed a magnetic dynamo. A magnetic field threads the interior and reaches into space. The field stores energy and channels charged particles. It shapes the behavior of the thin outer atmosphere. The result is activity. Darker spots appear where magnetic fields reduce the upward flow of heat. Bright flashes occur when magnetic loops reconnect. These are flares. A flare is a sudden release of stored magnetic energy. It heats the upper atmosphere and accelerates particles. It produces a burst of high-energy radiation and a spray of charged particles. Flares vary in strength and frequency. Young red dwarfs tend to flare more often because they rotate faster. As they age, they spin down. The magnetic field weakens a little, and flares become less common. Still, even old red dwarfs can flare. Magnetic fields do not vanish. They evolve. Around the star, the disk of gas and dust thins with time. The young star's radiation and winds blow away the remaining gas. What is left are planets, asteroids, and dust. Around red dwarfs, the region where liquid water can exist on a planet's surface lies close to the star. Close orbits are more likely to become tidally locked, with one side of a planet facing the star at all times. This locking depends on the planet's history. its mass, and the viscosity of its interior. Some planets keep a slow rotation, some lock. Atmospheres and oceans, if present, move heat around. Whether a world is stable for life depends on many details we do not yet know. But you can say that planets do form around many red dwarfs. We have measured their shadows as they pass in front of their stars. We have watched the starlight dim by a small, regular amount. We have seen the planets tug on their stars with gravity. The gentle pull shifts spectral lines back and forth. The planets are not guesses. They are observed. Around our red dwarf, it is reasonable that small rocky worlds could form in orbits of days to weeks. Ice-rich bodies could form farther out. The architecture depends on the early disk and how giant impacts and migration played out. In any case, the star is the long-term clock for the system. It sets the pace. Let us pause and zoom out for a moment. Our galaxy holds a vast number of stars. Most of them are red dwarfs. If you count them, they outnumber larger stars by a wide margin. Trillions of such stars light the spiral disk and the halo. They are dim individually, but numerous. If you looked at the Milky Way from the outside with sharp eyes, you would see that most stars are small and red. Their lifetimes are long compared to the age of the universe. The universe is about 14 billion years old. Many red dwarfs can live for hundreds of billions of years. The smallest can last for trillions. That means that most red dwarfs that ever formed are still shining today. They are cosmic long runners. Their light is modest. Their endurance is great. Now we return to our single star, which sits among countless cousins and carries on with its quiet work. Back at the star, the main sequence life unfolds with little drama. Fusion in the core converts hydrogen to helium through the proton chain, where two protons fuse to form deuterium, then helium-3, and finally helium-4. Each step releases energy. The rate is slow because the core temperature is relatively low compared to that of heavier stars. The slow rate is the reason the star lives so long. The core does not flood with energy. It keeps a calm pace. The outward pressure from the heat matches gravity without extra stress. The energy moves outward through convection. The time for a parcel of gas to circulate from the center to the surface and back is short compared to the star's lifetime. Mixing keeps the composition nearly uniform throughout most of the interior. The structure of a red dwarf is simple in this sense. There is no sharp boundary between a radiative zone and a convective zone. The transition from core to surface is continuous in its churning. That does not mean nothing changes. As hydrogen turns into helium, the average mass per particle increases. This change affects pressure. At the same temperature, helium provides less pressure support per particle than hydrogen. To keep balance, the core contracts slightly and warms a little. A slight warming increases the fusion rate, which increases the energy output. The star brightens slowly over time. The change is not quick. It is spread across billions of years. A planet with a long view would see the daylight become a bit stronger across deep time. Climates would respond if atmospheres and oceans are present. The star itself notices only through its internal adjustment. The process is steady. Hydrogen is consumed and redistributed by convection. Helium gradually accumulates, but not in a single central ball. It fills the interior like a dye mixed into water. Magnetic activity continues throughout. The star spins down as its magnetic field interacts with its wind. Charged particles carried away by the wind follow magnetic field lines, and remove angular momentum. The star's rotation period grows longer. A slower rotation weakens the dynamo strength. The number and size of spots diminish. Flares become less frequent, though they still occur. When a flare erupts, the outer atmosphere heats and expands. Radiation across many wavelengths increases for minutes to hours. If there are close planets, their upper atmospheres feel the extra energy. Molecules can be broken apart by ultraviolet light. The charged particles can erode atmospheres if the planets do not have protective magnetic fields, or if the star's activity is extreme. Over time, some planets lose gas while others retain it. The outcomes depend on initial mass, composition, magnetic shielding, and the detail of stellar activity. These are complicated, but the star's slow evolution gives planets time to adjust. No sudden bursts of luminosity change the basic rules of their heating. The star's light rises slowly. Flares are spikes, not a trend. The color and brightness of the red dwarf fit its surface temperature. It is cooler than the sun. Its visible light peaks toward red and orange hues. It emits most of its energy at infrared wavelengths. Its brightness per square meter is lower than that of a hotter star, but it also has less surface area because it is small. Both factors make it faint compared to sun-like stars. That is why it is hard to see with the naked eye unless it is very close to us. If you could approach it, you would find a compact star with surface gravity many times that of the sun's surface. The high gravity keeps the atmosphere thin and tight. The photosphere is a narrow layer where light escapes. Above it lies a chromosphere and a corona. These upper layers are heated by magnetic processes. They can be much hotter than the photosphere. The corona shines in X-rays. The level of X-ray emission tracks magnetic activity. As the star spins down, the X-ray brightness declines. The star ages gracefully. Inside, the physics is set by pressure, temperature, and composition. The equations that relate these are simple in form but complex in detail when you consider ionization, opacity, and energy generation. In our calm view, we can say this: higher pressure and temperature in the core allow fusion to proceed. The star finds a balance where the energy produced equals the energy lost at the surface. If the energy production rises too much, the core expands slightly and cools, which reduces the rate. If it drops, the core contracts and heats, which raises the rate. This negative feedback creates stability. A red dwarf is especially stable because the dependence of the fusion rate on temperature is gentle at the low temperatures where it operates. The star is not tightly wound. It responds softly to disturbances. We should consider timescales. The time to form from a collapsing cloud is short compared to its later life. A few million to tens of millions of years bring it from cloud to main sequence. After that, main sequence lifetimes stretch across hundreds of billions of years for the least massive red dwarfs, and tens of billions for the most massive red dwarfs, heavier ones in the red dwarf class. Our star, if it is near the middle of that range, will spend tens to perhaps 100 billion years on the main sequence. The universe does not yet have that history behind it. The universe is still younger than the lifetimes of these stars. That means our star, and many like it, have just begun their long central phase. They are still close to the conditions they had when fusion first settled in. The slow brightening is underway, but only a small part of the total change has occurred so far. If we zoom out again, we can ask what red dwarfs do for galaxies. They add mass to the stellar population. They contribute to the gravitational pull that holds gas and stars in the disk. They do not dominate the total light of a galaxy because they are faint, but they dominate the census of star systems. Their planetary systems are therefore common as well. When we count nearby stars with planets, a large fraction orbit red dwarfs. This matters for the long future. Worlds around long-lived stars have time for slow processes to unfold. Geological cycles and chemical changes on worlds can proceed without the star racing ahead to a transformative phase. A red dwarf's main sequence life is not a short preface to a dramatic end. It is the story itself. Back at our chosen star, the daily and yearly rhythms continue. Spots emerge and fade, flares flicker and subside. The wind flows. The light varies a little in step with activity. Over longer times, the rotation slows. There may be cycles of magnetic activity, with periods of higher and lower flaring. Some red dwarfs show such cycles, others do not, or their cycles are irregular. Observers collect light curves and spectra to watch these changes. The measurements build a record that reveals both the short bursts and the long glide. The record shows that a red dwarf does not sleep, but it does not hurry either. Its internal furnace burns at a rate that looks modest against the scale of more massive stars, but it is exact for its mass and structure. If the rate were lower, gravity would win and the core would heat until fusion rose. If the rate were higher, the core would expand and cool until fusion fell. Balance holds. Hydrogen fusion in a red dwarf follows the proton chain mostly through the low-temperature branches. This chain is slow because the first step, where two protons become deuterium, relies on the weak nuclear force. In plain terms, it is hard for two protons to become a proton and a neutron. That difficulty is a gift for longevity. The star's power output is throttled by that first step. Helium-3, an intermediate product, can fuse with itself in some cases. The exact balance of reactions depends on the core temperature and density. In red dwarfs, the core is not hot enough to strongly favor the faster branches that dominate in hotter stars. As a result, the energy generation is steady and not strongly concentrated at a single point. Convection spreads both the fuel and the products. No helium core grows to push new structural phases early in the life. Only when a very large fraction of the hydrogen has been consumed will the core conditions change enough to alter the star's state. That point lies far ahead. Let us think about how the star's brightness changes with time. At the start of the main sequence, the star has a certain luminosity and color. As helium accumulates, the core contracts slightly. The contraction raises the temperature, which increases the fusion rate. The luminosity rises by a modest factor across the main sequence life. The surface temperature changes a little, often warming slightly. The radius grows a small amount. The changes are not dramatic. They are slow and smooth. For a planet in the temperate zone, the zone moves outward slowly. A world that began just inside that zone may become warmer. A world that began just outside may enter it. If the planet has feedbacks such as clouds, ice, and greenhouse gases, these can adjust the climate. There is time for gradual shifts rather than sudden jumps. Again, the star sets the longest clock. At times, our star might partner with another star in a binary system. Many stars form in multiples. If our red dwarf has a companion, their gravity ties their motions together. The companion could be another red dwarf or a larger star. The presence of a companion can affect the disk during formation and the long-term behavior of planets. It can also affect rotation if tides act between the stars. But for the star's internal evolution, a distant companion changes little. The core still fuses hydrogen and the envelope still convects. The magnetic field still rises from rotation and convection. The steady, long life continues. We can also consider the chemistry that this star brings to future generations. Red dwarfs do not make heavy elements during the main sequence. They are not hot enough to fuse elements beyond helium. They do not enrich the interstellar medium in the way that massive stars do when they die in supernovae. Their role is to store gas for a long time, light their planets gently, and then, far later, return their mass in a cool, quiet way. That story lies ahead. During the main sequence, the mass stays bound. The wind carries only a tiny fraction away. The star keeps its material while it sips its fuel. In the present, the star's spectrum reveals its temperature and features of its atmosphere. Molecular bands appear where cooler conditions allow molecules to survive. Water vapor and titanium oxide can imprint their patterns in the light. Lines from neutral metals also appear. These features shift with temperature and gravity, letting astronomers classify the star. Red dwarfs span a range of subtypes from the warmer to the cooler end. Our star sits somewhere in this range, with its exact traits set by mass and composition. If its metal content is higher, the opacity in the atmosphere is higher and the structure adjusts. Metal-rich stars of a given mass can be slightly cooler and larger. Metal-poor stars are slightly hotter and smaller. The details are subtle but measurable. Rotation is one of the clearest signs of age in red dwarfs. Young stars spin fast. They show large amplitude variations in light as spots rotate across the visible face. Over time, winds carry away angular momentum and slow the rotation. The period lengthens from days to weeks and then to months for the slowest rotators. Using rotation as a clock is not perfect, but it gives a sense of age. If we watched our star for a long time, we would see its period drift longer. That drift is proof of the steady work of the wind and magnetic field. It says the star lives in contact with its environment, exchanging a tiny bit of angular momentum for stability. The star's habitable zone is close in, which shapes the possible climates of planets. Close orbits mean stronger tidal forces. Tides can heat interiors, maintaining volcanism, or even driving plate activity depending on the planet's size and structure. Tides can also synchronize spin and create large differences between the day side and night side. But thick atmospheres, oceans, and even ice transport can smooth those differences. Clouds can form on the warm side and reflect light, while winds move heat toward the cool side. If a planet has a magnetic field, it can deflect stellar particles and reduce atmospheric loss. The long, stable output of the star gives such systems a chance to find balance. The outcome is not predetermined. It is a set of possibilities guided by physics, chemistry, and time. From time to time, our red dwarf might pass through a region of the galaxy where interstellar gas is denser. The star's motion around the galaxy carries it through spiral arms and inter-arm spaces. Encounters with nearby stars are rare but possible over billions of years. The star's planets feel tiny tugs from passing masses. The outer debris belts can be stirred. The inner planets remain bound unless a very close encounter happens, which is unlikely. The star's main life is not disturbed by these journeys. It continues to fuse hydrogen and shine its steady light. If we compare our star to the Sun, the differences are clear. The Sun has a radiative core and a convective envelope. It builds a helium core that does not mix outward. It will leave the main sequence in a time span far shorter than the longest red dwarfs. The Sun's brightness rises more quickly. It will eventually swell and shed its outer layers. Our red dwarf will not do that while any other stars are still on the main sequence. Its path is slower and tighter. Its small mass keeps it cool. Its full convection keeps it efficient with fuel. These two facts give it a long future. Let us zoom out one more time, now with the dimension of time in mind. The age of the universe is still young compared to the long lives of small stars. Imagine the history of galaxies up to now as the first chapter of a long book. In the next chapters, the bright massive stars finish their short lives. Sun-like stars follow. Red dwarfs continue. They outlast their brighter cousins by wide margins. For many trillions of years, the typical star in the universe will be a red dwarf still on the main sequence or only beginning to leave it. Our star is part of that endurance. It is an example of the future's common light. We return again to the star's interior, where the small changes add up. The helium fraction creeps upward. The core contracts slightly. The fusion rate increases enough to keep pace with the surface losses. The surface brightens by a slow, steady percentage. If you could mark the star's luminosity with a ruler, you would need patience to see it move. But over an interval of billions of years, the increase is real. The convective mixing continues to bring fresh hydrogen inward. No insulating layer forms to protect a reservoir of unburned fuel. The star remains nearly uniform, which postpones the structural shifts that larger stars experience. Only when the hydrogen fraction is nearly used throughout will the core's physics change in a way that forces the star off the main sequence. That time lies in the deep future for our star. During all this, the star's gravitational field holds tight to its planets and debris. Comets and asteroids may fall inward and evaporate in the hot inner regions. Collisions continue in the debris belts, grinding some bodies to dust that the star's light slowly pushes outward. The mass lost in this dust is small. The system evolves, but the main mass remains. If there are planets, their orbits can shift slightly through interactions with each other. Resonances can form and break, but without a nearby massive intruder, the basic layout persists. The long life of the star gives orbital dynamics time to sample many configurations. Stability is often found because energy and angular momentum must be conserved, and large disruptions are rare. Observationally, astronomers can measure the age and activity of many red dwarfs and place them on a diagram of brightness versus temperature. There, the main sequence is a band that stretches from hot, bright stars to cool, faint ones. Our red dwarf sits on the lower right of that band. Its position drifts upward very slightly with time. The drift is the brightening we have described. Because the change is slow, populations of red dwarfs of different ages overlap in their positions. To estimate ages, astronomers also use rotation rates, lithium content in the youngest stars, and activity indicators. None are perfect. but together they tell a consistent story of slow evolution. You can also hear about the relationship between mass and luminosity. For red dwarfs, luminosity falls steeply with lower mass. A small change in mass leads to a large change in brightness. That relationship is rooted in the balance of pressure and temperature and the sensitivity of the fusion rate to core conditions. Our star's place in that relation sets its total power output and therefore its lifetime. Less mass means lower core temperature and slower fusion, which means longer life. More mass within the red dwarf range means a warmer core and a faster burn, but still far slower than sun-like stars. The line between red dwarfs and heavier stars is not a sharp wall, but a smooth transition in behavior. At this point in the star's life, which could be several billion years after formation, the system is quiet. The star has shed the last traces of its birth cloud. The planets, if any, move on regular paths. The star's wind and light establish a steady environment. The rate of change is slow enough that it feels like stillness. Yet in the core, nuclei meet and transform. Neutrinos speed away from those reactions, passing through the star and into space. Photons born in the core are absorbed and re-emitted countless times, then carried by convection to the surface, and finally stream away. Each photon's path inside is complicated. The overall flow is simple. Energy produced in the center leaves through the surface at a rate set by luminosity. If you could sit near the star and watch for a long time, you would come to trust that nothing sudden will happen. The only sharp events are flares, and even those are brief compared to the long quiet between. The story of this star is an exercise in patience. Gravity set the initial collapse. Heat built up until fusion could take over. Convection mixed the interior and kept the fuel accessible. Magnetic fields rose from rotation and convection and added texture to the surface and atmosphere. Planets formed from the leftover disk, and some of them endured. Then the star settled into a phase of stability that can last longer than any human language can name in a single word. We end this first part at a calm turning point that is not a change at all. Our red dwarf is on the main sequence, fully convective, slowly brightening, and still young compared to the time it holds ahead. The gas cloud has become a star. The disk has become a system. The flares come and go. The light continues. From here, the long central chapter stretches forward, and the clock of hydrogen will keep the pace. When enough of that fuel is gone, different physics will take its place. But not yet. Not for a very long time. The star has settled. Hydrogen fuses into helium in a core that is not a separate place, because the whole interior turns and mixes. Convection reaches from the center to the surface. Heat rises. Cooler gas sinks. Fuel flows inward and products flow outward. This circulation keeps the interior nearly uniform in composition, with only gentle gradients. The balance between gravity and pressure is firm. The star is round and compact. The surface is quiet, except for magnetic spots and the occasional flare. From the outside, it is a small red light with a steady heart. Time passes. Not years that anyone could count on a single page, but spans that require patient words. Billions of years pass. Then more billions add themselves to the record. The change that matters is slow. Helium makes up a slightly larger share of the gas than it did before. With each fusion reaction, two protons that once moved freely become part of a helium nucleus. The number of particles that share the pressure decreases. The mean mass per particle increases. The core responds by contracting a little and heating a little. That small rise in temperature nudges the fusion rate upward. The star brightens by a small amount. Then the process continues. The brightening is gradual. Over tens of billions of years, the luminosity creeps upward by a fraction that would be hard to notice in any short span. Yet the increase is real. The surface temperature may also rise slightly. The radius may grow a little. Convection still controls the transport of energy. The deep churning continues to bring fresh hydrogen inward. The star does not build a central reservoir of helium that sits unmixed. Instead, helium spreads. The interior becomes gently enriched everywhere. The change is like pigment mixing into water, not as a sharp core that swells and pushes outward. This keeps the structure stable and delays the end of the main sequence phase far beyond the lifetimes of heavier stars. The habitable zone responds to the slow brightening. It moves outward step by step, not because the star chooses to move it, but because the energy output grows. A planet that once sat in a temperate band might feel slightly warmer over long stretches. A planet that once lived just beyond the temperate zone might drift into it without moving at all. Everything depends on distance from the star, on atmospheres, on clouds, on oceans if they exist, and on the histories of those worlds. There is time for climates to adjust. There is time for surfaces to weather and for interiors to cool or to stay warm through tides. Nothing forces a sudden change. The star sets a slow pace that planets can follow. Rotation keeps easing. The magnetic field carries angular momentum away through a wind of charged particles. Each particle that escapes along a field line takes a tiny piece of the star's spin with it. Over time, these tiny losses add up. The rotation period grows longer. The dynamo that builds the magnetic field loses some of its strength as the differential motions that feed it weaken. Flares become less frequent and less intense on average. Spots grow smaller and do not cover as much of the surface. The corona emits less high-energy radiation. The spectrum shifts toward a calmer profile. Activity does not vanish. It becomes a quieter background. The star keeps its rhythm. If you stay with the star through a very long span, you see the cycles that observers often report. There are years of greater activity and years of lesser activity. There are patterns that repeat and patterns that break. The changes make sense in terms of magnetic fields that wind and unwind, that connect and reconnect, that store energy and release it. But underneath these variations, the main energy source does not falter. Fusion proceeds at a rate set by the balance of pressure and temperature, and the self-regulation of the core keeps it from drifting far from that balance. When production rises a little above what the surface is losing, the interior expands slightly and cools, which lowers the fusion rate. When production falls a little, the interior contracts and warms, which raises the rate. The negative feedback is simple and strong. Helium's rise continues. Helium does not burn during this phase because the temperatures are not high enough to fuse helium into heavier elements. The star is not massive enough for that outcome while hydrogen remains well mixed. Instead, helium accumulates as an inert product that affects pressure and therefore the subtle structure of the interior. Because convection is thorough, helium enrichment appears nearly everywhere inside. No sharp boundary forms. The fuel is not sealed away and wasted. This is the trait that gives red dwarfs their long lives. They use almost all of the hydrogen available, not just the gas trapped at the center. Efficiency stretches time. The planets age with the star. Closed worlds that formed from rock and metal may spin more slowly now because of tidal interactions with the star. Some may be locked with one hemisphere facing the star in permanent day and one in permanent night. Yet a dense atmosphere, if present, can transport heat and soften that contrast. Clouds may form on the warm side and reflect light. Winds may move heat toward the cool side. Volcanism may continue if tides or internal radioactivity keep interiors warm. Farther out, ice-rich worlds orbit beyond the temperate zone. Impacts continue but become rarer as debris is cleared. Occasional comets may scatter inward and then sublimate near the star, leaving a thin tail of dust. The star's light slowly increases. Planetary environments evolve to meet it. Now let us step away and compare. Around the galaxy, larger stars that were born at the same time as our red dwarf have already ended their main sequence lives. A few were massive and lived short, bright lives before exploding as supernovae. They left behind neutron stars or black holes and cast heavy elements into space. Their light was intense for a brief time. Now their remnants are small and dense and dark unless a companion feeds them. Many sun-like stars, born alongside red dwarfs in the same generation, have begun to swell into red giants. They brighten and become cooler at the surface, shedding layers of gas into the surrounding space. Their cores are growing helium-rich and dense. Some will ignite helium and burn it into carbon and oxygen for a time. Later, they will shed their outer envelopes and leave white dwarfs behind. Whole star clusters show this pattern when you map their members on a diagram of color and brightness. The bright turnoff point marches downward with age as heavier stars peel away. The red dwarfs remain on the main sequence band with no sign of departure. They keep their modest position and do not shift into the giant branch. When you compare many clusters of different ages, you see that red dwarfs are the constants in a field of change. The open star clusters that once dotted spiral arms have drifted apart under the pull of the galaxy's tides. Their stars are spread along orbits around the galactic center. Supernovae in the past enriched the gas between the stars. New generations formed with higher metal content. Spiral arms have come and gone in patterns set by density waves and the motion of gas. Through all this, the red dwarfs from the early days still shine. Their orbits may be perturbed by giant molecular clouds or close passes, but they remain intact. Some have migrated radially within the disk. Some have been pulled into the thick disk or even the halo after gentle interactions. The changes are real, yet do not alter their internal scripts. The red dwarfs continue unchanged in their central work of fusing hydrogen slowly. We return to our chosen star with a sense of context. It has outlived every massive star that shared its natal cloud. It will outlast every sun-like star from that same dawn. It does not grow arrogant, it simply persists. Its surface granulation still marks the upward and downward motion of gas in small cells. Its spectrum still shows broad molecular bands that belong to cool atmospheres. The chromosphere and corona still reveal activity, but the peaks are lower. The rotation period has stretched. If it was days in youth, it is weeks or months now, depending on the mass and wind history. Photometric variations are small. The light curve is almost flat with mild ripples. Inside the star, helium's fraction keeps climbing. Each rise in helium changes the equation of state in small steps and tweaks opacity. Opacity governs how hard it is for radiation to move through the gas. In a convective star, opacity still matters because it helps set the gradient that triggers convection. As composition changes, the threshold for convection remains easily met because of the low mass and cool temperatures. The whole star continues to turn over. A packet of gas in the deep interior is not destined to stay where it is. Over a modest time compared to the stellar age, it will rise and later sink. Through this constant motion, the star keeps itself mixed and resists the formation of a distinct, isolated core. The slow brightening carries consequences for the distribution of water on any temperate worlds. Ice lines shift, oceans expand or even evaporate depending on other feedbacks. Carbon dioxide cycles can adjust if the planet has geology that works like a thermostat. The pace is slow enough to allow reactions between rock, water, and air to work. The star grants both stability and time. In the outer system, ice-rich bodies may feel higher sublimation rates on their warm sides during close approaches if their orbits are eccentric. Dust from those bodies feeds faint rings or clouds that thin as gravity and radiation pressure rearrange them. The star's wind continues to sweep outward, carving a bubble in the local interstellar gas. That bubble breathes as the star moves through regions of higher or lower external pressure. But the wind itself declines with the magnetic activity, and the bubble's size reflects that change. Every so often, a flare reminds nearby planets that the star is not entirely quiet. A stored loop of magnetic energy reconnects and releases a burst. High-energy photons arrive at the planets in minutes. Charged particles follow. Upper atmospheres absorb and heat. Chemical bonds break and reform. For a time, the space weather near the star is rougher than usual. Then the field settles. The corona cools. The wind returns to its quieter state. Long-term averages continue to drift down as rotation slows further. The general story of declining activity holds. If you compare the cumulative light that the star releases across these long ages to the energy released by heavier stars over their short lives, you find that the red dwarf's total output over its full main sequence is large, even if its moment-to-moment power is modest. It is like a slow lamp that burns far longer than a bright torch. The average power never approaches that of a giant or supergiant, but the integral over time is impressive. This is why the red dwarf class contributes strongly to the long-term lighting of the galaxy, even though their contribution to current integrated luminosity is small. We can keep track of the star on the diagram that astronomers use, where temperature runs along one axis and brightness along the other. The point that marks our star slides slightly upward and a bit to the left over many billions of years, tracing a slow path as helium enrichment pushes the structure toward higher luminosity and slightly higher temperature. The change is gentle. There is no sudden leap to a different branch. The path has no hook or loop. It is a glide. The visible signature of this evolution is minimal in any human lifetime. The star looks the same to every generation that might watch it within any brief epoch. Meanwhile, changes beyond the star and its planets continue. The galaxy's star formation rate rises and falls with the supply of gas. Interactions with small satellite galaxies stir the disk. Bars form and fade in the center. The distribution of heavy elements grows richer in the inner regions and more slowly in the outer parts. Red dwarfs form in each new generation. The cumulative number keeps rising. They live on, while many of the bright blue stars that once lit star-forming regions have already died. In a remote future, the galaxy will be dominated by the endurance of these small stars. Their combined light will give the disk a steady glow, though that future is longer than words often try to handle. Back in the system of our star, the habitable zone has inched outward. A world that once sat in a comfortable band may now be on the warm side. If that world has a robust way to draw carbon dioxide from the air into rocks, such as weathering of silicate minerals and subduction, it may gradually reduce greenhouse warming and keep surface temperatures within a temperate range. If not, water may retreat to the poles or into the ground. The outcomes vary. The time scale is long. Life, if it ever took hold, would have time to adapt or move. If the system lacks such worlds, the shift remains a quiet geometric fact with no witness except the slow migration of a zone defined by physics. The star's rotation now is slow enough that the dynamo operates in a different regime than it did in youth. The magnetic cycle lengthens or perhaps fades into irregularity. Measurements of similar stars show that the relationship between rotation and activity follows a trend that flattens for very slow rotators. Our star moves along this trend, lowering its high-energy output and smoothing its variability. Polarized light from the star can betray the presence of large-scale magnetic fields, even as small-scale spots decline. Zeeman splitting in spectral lines remains as a sign of magnetism, yet the energy tied up in those fields is lower than before, and reconnection events are softer. In the interior, the proton chain continues. Two protons meet and, through a rare interaction, become deuterium. Deuterium fuses with another proton to make helium-3. Pairs of helium-3 nuclei combine to make helium-4. Or helium-3 can fuse with helium-4 in a path that depends on conditions. The balance among these routes depends on temperature and density. In our cool star, the branch that leans on helium-3 pairs is active. Neutrinos carry away a small fraction of the energy and fly out of the star unimpeded. Most of the energy stays as kinetic motion of particles and as photons that bounce and scatter until convection brings the heat outward. The rate of these reactions increases slowly with time as the core warms, but the increase is bounded by the feedback that maintains hydrostatic balance. Over tens of billions of years more, the composition shifts further. Helium's fraction rises toward a point where hydrogen becomes scarce everywhere. The star is not there yet in the middle of its long life. It has more hydrogen left than it has burned. But the future is set by the direction of the trend. Every fusion reaction moves the mix toward helium. Because the mixing is thorough, the depletion is global rather than central. In heavier stars, the core exhausts its hydrogen while the envelope still holds untouched fuel. In those stars, the core contracts and heats while the envelope swells and cools, and the star climbs into the giant branch. Our star avoids that path for a very long time. It must burn nearly all its hydrogen before a new structure can form. That requirement pushes the end far into the future. Let us zoom out with a clock in mind. The universe is still young compared to the full main sequence lifetime of small red dwarfs. Whole epochs of cosmic history have unfolded since the first stars lit. Galaxies assembled, heavy elements built up, planets formed. Civilizations could rise and fall on worlds around many kinds of stars. Through all that, our red dwarf has continued its steady burn. In the time it has taken for larger stars to swell and shed their layers or collapse in violent ends, the red dwarf has altered its brightness by small fractions. It is not indifferent because it brightens and ages. It is simply steady enough that changes rarely matter over short slices of deep time. Neighbors change. Passing stars shift the shapes of outer debris belts. A rogue cloud of gas may drift near and add a faint glow to the sky of any worlds looking outward. Comets may be nudged onto paths that graze the inner system. Still, the star endures with the same physical core. Gravity holds it tight. Pressure from heat and radiation balances that pull. The mean free path of photons in the interior is short compared to the size of the star, but convection moves energy more effectively than radiation could. The turbulent motions rise and fall in large cells that carry heat outward. When those motions reach the surface, they leave fine structure in brightness and spectra that speaks to instruments built to hear these quiet signals. If the star has a companion, tides have long since sculpted their spins if the orbit is close. If the companion is distant, the tides are weak and spins evolve mostly under wind losses. A close binary of two red dwarfs could exchange small amounts of mass through winds, but would not share a common envelope unless the separation is extremely tight. The ordinary case is separation wide enough that each star lives as if alone in terms of internal evolution. Our focus remains on the single star we began with, whether solitary or gently coupled by gravity to a partner that does not disturb its interior. In this long middle passage, observers in a far future could assemble a record of the star's slight brightening and slowing rotation by comparing archives taken over many ages. The evidence would be clear in data, but subtle to any single watcher. Spectra would show a trend toward weaker chromospheric lines that mark magnetic heating. X-ray fluxes would sink. Ultraviolet lines would fade. The infrared output would rise slightly in step with the total luminosity increase. These are modest moves along well-understood paths. It is worth thinking about the star's store of angular momentum and how it compares to the energy of fusion. The star's spin energy has been leaking away through magnetic braking since youth. The fraction lost grows with time. That loss does not affect the star's structure much because the rotational energy is small compared to the thermal and gravitational binding energies. The star could stop spinning and still maintain hydrostatic equilibrium with almost no change in radius or luminosity. But the spin matters for magnetism, and magnetism matters for planets. The slow rotation of middle and late ages brings space weather into a quieter regime. The planetary atmospheres that have endured flares and winds during the first billions now experience gentler conditions. In the planets themselves, mantle convection cools in a slow glide unless tides or radiogenic heating sustain it. Magnetic fields in planets, if any, may weaken as cores crystallize or as heat flows change. Orbits may exchange eccentricity and inclination through resonant interactions, then settle again. Collisional families in asteroid belts evolve. The possibilities are many, but the stellar influence is one constant curve that rises gently. The point approaches when hydrogen becomes truly scarce throughout the interior. Not now, not soon in human measures, but it is visible in the equations. As the helium fraction rises, the central temperature creeps up to keep fusion going at the rate demanded by the surface losses. There is a limit to how far this can continue under the same structure. Eventually, when the share of hydrogen drops low enough, the star must adjust in a deeper way. The core will no longer be able to maintain the same fusion rate simply by small contractions and small temperature rises. The response will be to change how the interior supports itself. The star will begin to leave the exact conditions of its long main sequence balance. The shift will be slow in a red dwarf because the remaining hydrogen continues to burn and because convection keeps supplying what is left. But the direction is set. Before we reach that point, the star spends more long ages in what looks like the same state. The brightness increases by small steps. The spectrum cools or warms slightly depending on the exact mass and composition. The radius grows a little. The mixing continues with unbroken reach. The interior composition keeps drifting toward helium. Activity fades further. Flares become rare and mild. The wind thins. The habitable zone keeps moving outward at a steady pace that is slow compared to most processes on planets, but steady enough to build trends. Now we zoom out once more, not to watch other stars die, but to place our star along the timeline of the universe. Many of the brightest stars that now shine will be gone long before our red dwarf finishes its central phase. Stellar nurseries may grow quiet as the supply of cold gas in the galaxy declines. The disk may thin. The rate of new star formation may fall. The balance of light will shift toward older populations. Red dwarfs will continue to contribute their small, patient glow. In that far context, the persistence of such small stars becomes the theme of the sky. We return to the single star and move close again. The surface shows a calm granulation pattern. Spectral lines sit where we expect them. The star gives off most of its energy as infrared light that our eyes do not see, but detectors would register as a stable output. The star's radius is small. Its mass is small. Its gravity at the surface is high because the mass is packed into a compact volume. The scale height of the atmosphere is short, so the photosphere is thin. Above it, the chromosphere and corona still exist, but they are faint compared to youth. The outer layers hold less stored magnetic energy. Flares can still occur, but the typical release is modest. The inner convection is the star's long-lived habit. The turnover time is short compared to the age, so countless cycles have taken place. Each parcel of gas has made many journeys up and down. In doing so, it has shared in the fusion of hydrogen and the transport of heat and helium. If you follow a parcel, you find that it is not special. It becomes part of a continuous flow that makes the whole interior behave as one. This is what allows the star to avoid the core envelope split that leads other stars to move off the main sequence earlier. The price for that efficiency is time. The star cannot move to a new phase until it has nearly exhausted its hydrogen everywhere. The planets continue their patient orbits. In some of the inner worlds, if they exist, the geology may be quiet now if internal heat has dwindled. If tides are strong, heat may continue longer. If a planet has moons, tidal exchanges within the planet-moon pair may shape rotations and orbits. If there is a large planet farther out, resonances can tug on smaller bodies and reshape belts. The system is simple in outline, but full of slow-motion detail. Through it all, the red dwarf gives the same modest light with a slight upward trend. At intervals, a meteor shower would sweep across any sky on a world with air, as debris streams intersect the orbit. On airless bodies, impacts make new craters that record timing one by one. dust coats surfaces. Ice forms and sublimates with seasons if tilts and eccentricities permit seasons. The source of heat remains the star, and its increase is measured in small steps across long spans. The magnetic field of the star now is stable in the sense that it does not surprise with new modes. It follows the rules of a slow dynamo. The field flips polarity perhaps, or perhaps it becomes more static, depending on the exact rotation and convection profiles. The polar regions and equatorial regions share magnetic lines that reach into space and guide the wind. Radio emission from the star weakens, but can still reveal auroral processes in the stellar atmosphere. Planets with magnetic fields of their own produce auroras when stellar particles reach them. The color would depend on the gases in the air. The intensity would depend on the star's activity and the planet's field strength. As we approach the next threshold, the star's response to helium enrichment grows more noticeable if you could look with instruments that compare one age to another. The core's temperature climbs by small amounts, but now those small amounts matter more because the fraction of hydrogen is lower. The feedback that has held the star in balance still works, but the adjustments become a bit larger for the same change in composition. The curve is steepening. The star keeps pace because there is still hydrogen left to fuse, and convection still feeds the center with what remains. Now we can ask a simple question that carries us into the last part of this phase. How does a star like this signal that the main sequence is ending? The answer is not a sudden flare or a change in color that any eye would catch. It is a slow turn in the trend lines of the interior. The core begins to build a region where pressure support relies more on the quantum behavior of electrons than on thermal motion. This happens only when densities climb and temperatures rise in a way that the previous regulation cannot fully stop. In heavier stars, this shift happens when the core runs out of hydrogen while fuel remains unused in the envelope. In a red dwarf, the change waits until the hydrogen is scarce almost everywhere. Our star is not yet there, but it is approaching. The exact timing depends on mass and metal content. A slightly more massive red dwarf reaches this point earlier in absolute time than a slightly less massive one, though both timelines are long beyond ordinary measures. The path forward will keep the star stable while any significant hydrogen remains. The star will continue to brighten slowly. The helium fraction will continue to rise toward a near total share. The convective profile will adjust. The wind will weaken further. Space weather will soften. Planets will keep aging. The habitable zone will keep sliding outward. We can pause here. The picture is clear. A small star has passed through the middle of its long life without leaving the main sequence. It has brightened by gentle steps. It has mixed its interior and used its fuel with care. Its magnetic activity has faded while rotation has slowed. Its planets, if any, have evolved with it under a stable, rising light. Around the galaxy, larger stars have swollen and died. Suns have become giants and shed their skins. Compact remnants have cooled. Through all of that, the red dwarf has held its place and kept to a simple rule. Fuse hydrogen at a slow rate. Mix the interior so no fuel is left unused. Adjust to helium by small contractions and small warmings. Repeat for ages that exceed the age of most other things. The next change is not a leap. It is a turn that starts almost invisibly. Hydrogen becomes scarce enough that the old balance begins to strain. The core's response grows stronger. The star is still steady, still quiet, still red, It is beginning to prepare for a future in which hydrogen is no longer the easy answer. That preparation will unfold over a time so long that words stretch thin. We stop at that quiet point, with the star easing toward a new chapter that has not yet started, while light from the main sequence still fills space and sets the pace for everything around it. Hydrogen is now scarce everywhere, not just in the deep center or the outer layers, but through the entire interior. Full convection has carried helium outward and moved what hydrogen remains inward, but the supply keeps falling. The star still tries to keep the old balance. The core contracts a small amount and warms a small amount to raise the fusion rate to match the light lost at the surface. This has worked for a very long time. It still works for a while, but the adjustments start to fall short. There is not enough fresh hydrogen in reserve to maintain the same production with the same structure. The self-regulation that once held so easily begins to strain. The fusion rate drops, not in a sudden fall, but as a gentle decline measured across ages that exceed the entire history of bright, heavy stars. The core contracts more than before. Contraction releases gravitational energy as heat, but the added heat does not fully replace the falling power from fusion. The star begins to change in a slow, coordinated way. The outer layers respond to the weakening core by adjusting their pressure and temperature. The whole star feels the shift. The radius starts to shrink a little. The surface cools a little. Luminosity begins a long, shallow fade. Inside, a new kind of support begins to matter. The gas has grown denser as the core contracts, and the matter there begins to behave in a way that does not depend only on temperature. The electrons pack closely enough that their quantum behavior provides pressure even when heat is not high. This electron pressure adds to the thermal pressure and helps hold gravity in check. It does not ignite a new source of energy. It does not create more light. It acts as a silent cushion that slows further contraction. The star remains stable, but the character of its stability is no longer the same as it was on the main sequence. Helium fusion does not begin. The star is not massive enough to raise its core to the temperatures needed for helium nuclei to combine. No run of gentle contraction will bridge that gap. The star's path does not cross into the giant phases that heavier stars reach when their cores exhaust hydrogen. There is no swelling into a cool, bright giant. There is no pulsing shell that throws off layers into space. The red dwarf instead turns its long story toward a simple end. It will become a compact remnant supported by electron pressure and will slowly cool with time. This turn does not happen in a season or in a single lifetime of a world that might be circling the star. It plays out over ages that stretch longer than the histories of galaxies have so far. The star keeps fusing hydrogen as long as there is any to be found in its mixed interior, but the rate is low and falling. The fraction of hydrogen keeps dropping. Helium continues to rise. The convective churning still moves material, but each sweep brings less fuel to the center. There is no new supply to change that trend. As the radius contracts, the surface gravity grows stronger. The atmosphere tightens. The photosphere, where light escapes, settles a little deeper. The surface temperature adjusts. For a time, the mixture of composition and contraction can warm the surface slightly, but the overall luminosity continues to fall as the fuel supply dwindles. The star's color may drift toward the blue in the late stages of hydrogen burning because the interior becomes more transparent and the mean particle mass rises. But this is a subtle phase in a long path. The lasting trend is a decline in power output. In the end, light must follow the energy available. Planets that have kept pace with the star's long middle life now face a slow cooling. The habitable zone that once drifted outward with the brightening now drifts inward as the star dims. A world that warmed may now find the sunlight easing down. If air and water remain, ice lines creep outward in winter and survive deeper into summer. If greenhouse gases have been drawn into rocks, they may return to the air if volcanoes still work. If tides still warm interiors, that heat can continue while the sky grows darker. Worlds farther out feel the decline first. Close worlds, if any, remain tidally shaped and steady, but their day side cools and their night side falls even colder unless thick air softens the contrast. Every path is slow. The star never jerks the climate. It dims a little more each long step. Magnetic activity has weakened to a background state. The rotation is slow. The dynamo runs at a low setting. Flares are rare and small. The wind is thin. The coronal temperature and density are low compared to youth. High-energy radiation is faint. Space weather settles into a quiet mode that gives planets little trouble beyond the gentle pressure of a slow wind. The magnetic field still shapes charged particles near the star. It still opens and closes field lines with small reconnection events. But all of this is soft. The star is easing past the need to lose angular momentum because there is little left to lose. Deep in the interior, the core grows more degenerate in the technical sense. Electron pressure carries a larger share of the weight. The temperature can fall while pressure remains high, which is a change from the gas behavior that dominated the main sequence. When heat no longer controls pressure, the link between temperature and support is loosened. The star can cool without collapsing. That shift seals the future. Once fusion stops entirely, the object will persist as a compact, cooling body with no internal heat source except the stored heat left from its long life. As hydrogen drops below the level needed to sustain a global fusion rate, shell burning tries to continue in the regions where a little fuel still reaches fusion temperatures. But full convection in such a low-mass star blurs the line between core and shell. There is no massive envelope to swell. There is no staircase of advancing burn zones. The small star contracts and settles toward a remnant in direct steps. The last hydrogen fuses and becomes helium. The interior cools. The light fades. At this point, we can step back and look around at what remains in the wider sky. The bright, massive stars are long gone. They lived briefly and died early. Their remnants are neutron stars and black holes that hide their presence unless they feed on nearby gas. The mid-mass and sun-like stars are gone as well. They swelled into giants, shed their outer layers into shells that briefly glowed, and then became white dwarfs. Those remnants have been cooling since. The overall light of galaxies has already faded. Star formation has slowed because the gas that can make new stars has been consumed or heated or dispersed beyond the ability of gravity to bring it together. In this aging universe, the steady survivors are the red dwarfs that are still on their late main sequence or have only begun their quiet fade. Among these survivors, our chosen star is one of many. The combined glow of countless small stars gives galaxies a soft light that changes only slowly. The color trends toward red and infrared. The energy that fills space is gentler than before. Dust still shines faintly where older stars warm it. The central black holes of galaxies persist, but with little fuel, they remain quiet most of the time. The sky is peaceful. In this future, the common experience across the cosmos is the modest light of small stars and the long cooling of their remnants. Back with our red dwarf, the last stages of hydrogen use pass. The final fusions occur here and there in regions where temperature and density are still high enough. The overall power output has become small. The star is now mostly helium by mass, with trace amounts of heavier elements that were present from its birth cloud. There is no path upward to new burning stages. The physics is clear on this point. The star lacks the weight to compress and heat the core to helium ignition. It will not become a giant. It will not cast off a bright shell. It will not pulse. It will ease into a stable, compact form and then cool. The transition is slow and simple. Contraction continues until the remnant reaches the size set by electron pressure for its mass. The star becomes a white dwarf of helium composition. Its radius is small, comparable to a planet, but with far greater mass. The surface gravity is intense. The outer layers are thin and tight. The interior is supported by the pressure of electrons squeezed into a dense state. The whole object is hot at birth, not from fusion, but from the leftover heat of contraction and earlier burning. It shines by releasing that stored heat through its surface. No engine burns inside anymore. The color of the remnant depends on its temperature. At first, it glows white or blue-white because the surface is hot. Over long stretches, it cools and its color shifts through white to yellow, then to red, and finally into infrared as the light slips beyond what human eyes can see. The cooling takes a time so long that it becomes the main clock of the remnant's life. The atmosphere of the white dwarf sorts itself by weight. The lightest elements float upward. If any hydrogen remains, it forms a thin skin. If not, helium forms the surface. This thin layer controls how the remnant loses heat, because different gases leak heat in different ways. The slope of the cooling curve depends on the surface mix, mass, and how crystals form in the interior as it cools. As the white dwarf cools, the dense matter inside begins to arrange itself into an orderly state. This crystallization releases a small amount of heat, which delays the cooling for a time. The process continues from the center outward as temperatures fall. The remnant grows more rigid inside while the surface light dims. None of this is dramatic. There are no outbursts or sudden shifts. The object simply radiates its heat away and moves down the long slope of temperature and brightness. The planets respond again. Any that remain bound now orbit a compact, faint star. Their years change little, but their days grow colder. If a planet passes close enough, tides can reshape it. If the contraction of the star and the changing mass loss have altered orbits slightly, new resonances can arise among the surviving bodies. The inner system may be harsh. If any object moves too near, the strong gravity can pull it apart. Debris can form a ring for a while before slowly raining down. Farther out, icy bodies become more stable against sunlight and hold their volatiles in deeper cold. The entire system grows dim and quiet. We can widen the view again and look at the universe during the long cooling of this remnant and its kin. The cosmic background has cooled further. The expansion carries galaxies away from one another. The light from distant corners stretches to longer wavelengths and fades below easy detection. Local groups of galaxies remain bound. Their stars are mostly old and faint. White dwarfs cool. Neutron stars cool. Black holes persist. The energy budget of the sky comes down to long wavelengths from cool surfaces and the occasional flare of a rare interaction. Red dwarfs that were younger than our chosen star continue their main sequence lives in this era. They are the last true stars that still fuse in their cores. They offer the last steady starlight for observers who might be there to see it. Their planets feel a warmth that still follows the old rules. Their habitable zones still exist if any worlds wait inside them. These red dwarfs are the final long burners. Over time, even they run short of hydrogen. Each one shifts to the same quiet end. Each one becomes a white dwarf and begins to cool. It is natural to wonder how long the last lights endure. The answer avoids simple words because the numbers stretch far beyond familiar scales. Cooling white dwarfs fade across spans that reach into deep future ages. The light becomes too faint for most instruments before it reaches zero. The remnant continues to exist, holding its heat in a dense body that cools step by step toward the temperature of its surroundings. In that far future, a cold, dark body of the same mass still holds the memory of its long history in its composition and structure. There is nothing tragic in this path. It is a working out of gravity, pressure, and quantum rules. A small star used its fuel with care for a long time. It did not flare into a brief, bright end. It did not break apart. It carried its matter from cloud to star to remnant with quiet continuity. The end is not a stop, but a settling into a state that can last as long as the universe allows. Let us return to the white dwarf that our red dwarf has become. The surface is smooth and thin. The gravity is strong enough that mountains would be microscopic. The light you see from it comes from a layer only a small distance deep. Below that lies a sea of dense helium. Crystals form as temperatures drop. The atmosphere filters and spreads the light, with features that reveal the elements present. Spectra show broad lines that pressure has widened. The shape of those lines and the color of the continuum tell you the temperature, gravity, and composition. Observers who keep records across long ages can plot the steady decline and place this remnant on a curve that others follow. The surroundings of the remnant may hold clues to the system's earlier life. Rings made of dust may glow faintly in infrared light if bodies have been torn apart. Small planets may still circle at safe distances. Their surfaces are dark and cold. Their skies are black. Any heat they keep comes from their own interior radioactivity or tides, if any remain. On a world with an atmosphere, the sky would hold a star that is small and sharp without the deep color it once had. The rising and setting of that small light would mark the long days in a cold age. Beyond this single system, the last generations of red dwarfs keep up their quiet burn. They have outlived every other kind of star by a wide margin. They carry the epilogue of stellar time. Their accumulation was large because many formed and almost none died. In the deep future, they are the common stars not only by number, but by presence. Their light fills the remaining night where galaxies still hold together. The universe is not empty. It is slow. As more red dwarfs finish their main sequence lives and become white dwarfs, the balance shifts again. The last fusing stars disappear. The sky becomes a landscape of remnants cooling in silence. Black holes remain as centers of gravity. In clusters and groups, some remnants may wander too close to a black hole and be torn apart, releasing a brief flare of light. Such events are rare and do not reverse the general fade. Dark energy continues to separate bound islands from one another. Within each island, the population grows older. Through all these stages, the story of our original star is complete. It formed from a cold cloud. It contracted under gravity. It warmed until hydrogen could fuse. It settled onto the main sequence as a small, fully convective star. It brightened slowly for ages, while its rotation slowed and its magnetic activity declined. It used its fuel with care because mixing allows access to almost all the hydrogen. It did not build a central reservoir that forced it into a rapid change. Only when hydrogen became scarce everywhere did it begin to alter its shape and support in a lasting way. It dropped its fusion rate. It contracted. It cooled. It became a white dwarf. It now glows by stored heat and cools with a patience that matches the timescale of a universe growing old. We can bring the view back to the scale where a single point of light matters again. Imagine a night sky, long after the ages of bright star birth and brilliant deaths. A small, steady light shines among the faint traces of others. It is a red dwarf still burning, or a fresh white dwarf newly cooling. All around, the space between bound groups has stretched so far that distant galaxies have faded from easy sight. Local stars carry the scene. Among them, the last red dwarfs are the true stars that still fuse. Their light is modest and calm. Their clocks turn slowly. They keep the final era of stellar time. If we start there and slip backward in memory, we find our original red dwarf again, now in the present of its own long story. We see it during the final stages of hydrogen use. We see the gradual contraction. We see the surface cooling and the light dimming as the fusion engine winds down. We see the gentle handover from thermal pressure to electron pressure in the core. We see the ending of fusion without the start of a new burning phase. We see the compact remnant form. We follow it as it cools and becomes quieter with every span of time that passes. The simplicity of the end invites one last comparison. Heavier stars change state through dramatic episodes because their cores stratify and their envelopes respond in large ways. They flash into giants and shed matter. They explode. They leave behind cores that were once the inner part of a complex structure. Our red dwarf never built such a layered center. It could not jump to new fuels because gravity and mass never pushed the core to the required temperatures. It had one long phase of fusion and one long cooling afterward. The path is quiet because the physics and the mass point that way. There is humility in that path. The star did not aim for endurance. It simply followed the rules written into its structure. Gravity gathered it. Pressure supported it. Convection mixed it. Fusion warmed it. Magnetism textured it. Time carried it. When the fuel was gone, quantum pressure held it together. That sequence does not need drama to be complete. It is already the whole. If we take a last wide view, we see the universe far beyond any present age. All massive stars are gone. Sun, like stars, are gone. The red dwarfs that formed later than our chosen one carry the last phase of starlight. For a long while, they keep their steady burn. Then, one by one, they too finish. White dwarfs cool. Neutron stars and black holes keep their gravity. The energy of the sky moves to longer wavelengths and lower brightness. The cosmos grows older without haste. The final word of ordinary starlight belongs to red dwarfs because they live slowly and use what they have with care. We end where we began. A small point of light holds its place in a quiet sky. It is easy to overlook. It has carried a long story from a cold cloud to a calm remnant. Its beginning was slow. Its middle was steady. Its ending is patient. The light that reaches you came from a surface where heat meets space. Behind that surface lies the memory of gravity, pressure, fusion, mixing, and time. The red dwarf keeps its place in the history of the universe as a long, modest flame, and then as a fading ember. The story closes with a quiet star that has done its work and rests in the dark, while the night around it grows older and still.